Hello, today I'm presenting the system design for OrateIQ, an AI-powered public speaking coach. This project demonstrates design principles, domain modeling, design patterns, and cloud architecture. I'll walk you through the problem, the solution architecture, key design decisions, and the patterns and principles that shape the system. Let's start with the problem we're trying to solve. So public speakers today lack objective, scalable feedback mechanisms. They rely on self-assessment, which is biased, or peer feedback, which is time-consuming and inconsistent. What's missing is objective measurement of delivery, pacing, tone, clarity, combined with actionable feedback and progress tracking over time. The system addresses this with 4 key features: speech recording and upload, AI-powered analysis using speech-to-text and LLMs, human evaluator feedback to complement the AI, and goal setting with progress tracking. The target users are public speakers seeking improvement and evaluators like coaches or peers who provide guidance. The solution uses a layered, event-driven architecture deployed on Azure. Clients interact through an API gateway that routes to a modular monolith API application. The API handles synchronous operations, upload, queries, and publishes events to a message bus. 5 background workers consume these events for long-running tasks including speech-to-text transcription, analysis, AI feedback generation, progress tracking, and notifications. This decoupling is critical since these calls can take anywhere from 5 to 60 seconds depending on the size of the recording, so we cannot block requests. The use case diagram shows the system's actors and their interactions. So public speakers interact with 4 use cases: recording speeches, getting feedback, setting goals, and tracking progress. Evaluators submit human feedback to complement AI analysis. Supporting actors include the authentication system for secure access, speech-to-text for transcription, an LLM for AI feedback generation, and a notification service for alerts. Each use case has a detailed system operation contract for defining responsibilities, preconditions, and postconditions. These SOCs became the foundation for class design and the implementation. Now let's take a look at how information flows through the system. So when a user uploads a speech, the synchronous flow is fairly straightforward. The controller validates the audio, the service stores it in blob storage, creates a speech record, and publishes a speech uploaded event. The user gets immediate confirmation, then async processing begins. So the async processing workflow is the heart of the system. The speech uploaded event triggers the STT worker, which calls Azure Cognitive Services to generate a transcript and publishes the transcription created event. The analysis worker consumes that event, analyzes speech metrics like pacing and filler words, and publishes the speech analysis created event. The feedback worker then calls the LLM to generate personalized feedback and publishes the feedback created event. The progress worker updates goal tracking, and finally, the notification worker alerts the user. This flow demonstrates the observer pattern. Workers are loosely coupled, subscribing to events independently. It's also a chain of responsibility. Each worker handles its stage and passes control to the next. It also uses the strategy pattern for external services, so the STT and LLM interfaces allow swapping providers without changing business logic. The architecture also provides fault tolerance, so if a worker fails, messages stay in the queue and retry. It enables independent scaling, so if a transcription, for instance, is the bottleneck, we just scale the STT worker. Now let's see how the speech objects transition through the states. So a speech object transitions through multiple states as it's processed. The happy path is uploaded, transcribing, analyzing, generating feedback, feedback ready, and eventually archived. If any step fails, we have dedicated error states: transcription failed, analysis failed, feedback failed, each with proper logging and user notification. This granularity is critical for recovery. If transcription fails versus feedback generation fails, the recovery logic is different. The state machine ensures that we never lose track of where speech is in the pipeline and provides observability. Users can see real-time the status updates. Now we'll take a look at the domain model, which centers on three aggregate roots: the speech, user, and goal. Speech is the core entity. It composes audio metadata, transcript, and speech analysis. Speech aggregates feedback, so there many feedback records can reference one speech. Feedback uses inheritance, an abstract base class with two concrete types, AI feedback and evaluator feedback. The goal tracking works through progress snapshots, which link a goal to a feedback entry at a specific point in time, which enables historical progress tracking, for example, so we can see how a speaker's pacing score improved over 10 speeches. Next, we'll take a look to see how this maps to the class diagram. So the class diagram shows a layered architecture with clear separation of concerns. At the top, controllers handle HTTP requests, speech controller, feedback controller, and so on. The controllers are thin. They validate input and delegate to services. The application layer contains services for business logic and workers for background processing. The services encapsulate all operations related to their domain entity. So speech service handles everything that's speech related. Workers orchestrate async workflows. Crucially, every dependency is interface based, so controllers depend on iSpeech service, not the concrete implementation. External services like speech to text, LLM, and storage are abstracted behind interfaces. This follows the dependency inversion principle, so high-level modules don't depend on the low-level details. Both depend on abstractions. This design enables testability. We can inject mock repositories and services. It also supports flexibility. We can swap out Azure Cognitive Services for Google Speech to Text without changing any business logic. And it's also microservices ready, so clear module boundaries with interface-based communication. The solid principles are baked in, single responsibility. Each class has one reason to change. Now we'll take a look at the component diagram. So the component diagram shows how the system's physical components are organized and their dependencies. Client interacts through an API gateway that provides a single entry point, routing, and rate limiting. The gateway routes to controllers in the presentation layer. The controllers depend on service interfaces, not the implementations. Services in the application layer depend on repositories for data access, the message bus for events, and the external service interfaces for the STT, LLM, and storage. Workers also live in that same application layer. They consume from the message bus and call external services. And the infrastructure layer provides concrete implementations. Key patterns include API gateway for centralized routing, repository for data abstraction, adapter for external service isolation, worker for background processing. Repositories in the message bus mediate coupling, enabling loose coupling and testability. Now let's take a look at how this can be deployed to Azure. So the system deploys to an Azure Kubernetes service using security-first architecture. The network uses 4 subnets: a public subnet with an application gateway for DDoS protection, 2 subnets for the API and background workers, and private endpoints for all data services, so for 0 public IPs. This is critical since voice recordings are biometric data under GDPRs. Data services include the Postgres SQL for transactional data, Redis for caching, Service Bus for async messaging, and blob storage for audio files. The security is layered. We have private endpoints, encryption everywhere, rate limiting to prevent abuse. The architecture scales horizontally. API pods autoscale on CPU, workers autoscale on queue depth. This supports 100,000 users and 10,000 requests per second. The philosophy here is to start simple with a modular monolith and scale incrementally. So clear module boundaries and event-driven communication enables microservice extraction when needed. Now let's talk about the design patterns. The design applies graphs, solid, gang of four, and architecture patterns throughout with clear justifications. Graphs principles include information expert, transcript, calculates its own word count, low coupling, the API publishes events instead of calling workers directly, enabling independent scaling, high cohesion, speech service encapsulates all speech operations, polymorphism, the feedback hierarchy handles both AI and evaluator feedback without type checking. Then over for solid principles, we have the single responsibility, controller services, and repositories each have one reason to change. Open closed, we can add new feedback types without modifying existing code. Dependency inversion, so services depend on abstractions like the iSpeech repository, not concrete implementations. Then for the gang of four patterns, we have repository abstracts data access. Strategy enables pluggable STT and LLM providers. So like I mentioned before, we can swap out Azure for Google without changing business logic for those providers. Observer powers the event-driven architecture, and we have adapters for which wrap the external SDKs. For architectural patterns, we are using a layered architecture for separation of concerns, event-driven for async processing, and modular monolith for simplicity with clear microservices extraction path. So every pattern choice ties directly to requirements: scalability, maintainability, testability, and security. To conclude, I've presented a comprehensive system design for OrateIQ, an AI-powered public speaking coach. The design includes 5 use cases with system operation contracts, a complete set of UML diagrams, and a security-first Azure deployment supporting 100,000 users and 10,000 requests per second. Design principles applied: grasp for responsibility assignment, solid for maintainability, gang of four patterns like repository and strategy, and architectural patterns like layered and event-driven architecture. Every decision has a justification: event-driven for long-running operations, granular state machines for observability, private endpoints for GDPR compliance. Key takeaways were: domain modeling drives design, the design patterns solve real problems, not applied for their own sake. Security and scalability are design concerns, not afterthoughts. Modular monoliths are a pragmatic, clear extraction paths without premature complexity. This project taught me to think like an architect, designing systems that are secure by design, built to scale and ready to evolve. I think that's the difference between writing code and engineering solutions, and that's the approach I'll bring to every challenge in my career. Thank you.